it here, corresponds to like half your observed wavelengths, then you have destructive interference. So what you observe is like such a pattern where you have a very very high maximum in the center of your observation, and then if you go out, you have these diffraction rings. So this is the typical Fraunhofer diffraction. And so what you observe, if you observe a star with a telescope, the shape of the star, the intensity shape of your star on the detector will look something like this. And this actually affects how many stars we can observe. So let's assume we observe 2 stars, and they both make this diffraction pattern on our detector. And if we move the stars closer and closer together, so starting from a difference that's actually 2 times the diameter of our first maximum, then we see that we can still separate the 2 sources. But now we move them together, and we see that they at one point become indistinguishable. So, and at this point we couldn't tell anymore that it's actually 2 stars that we observed, but we would observe them as 1 star. And the problem gets even worse if one star is brighter than the other one. So here we have this faint star down here, and as soon as it comes closer to the bright star, you don't see it anymore. So, so one aim of our observations is, of course, trying to make this as sharp as possible, so that we can still observe stars at very small distances towards each other. And so how do we measure now the spatial resolution of a telescope? It's defined by the full width at half maximum. So if you look at this, this is again showing you the intensity profile of an observed star. What we look at is half the maximum, at half the value of the maximum intensity here, and measure the width of the profile there. And this is the full width half maximum. And what determines it